Hello, everyone. My name is Devin Peterson. I'm a faculty member in the Department of Food Science Technology at The Ohio State University. My area of research is flavor chemistry, and so today I'm going to be talking about some of our work focused on, and as you can see here, flavor challenges related to pea protein ingredients and sort of maybe ideas of how do we understand these materials in a better way to help with, you would say, new product innovation. So, a little bit, I think, probably intuitive to most people, but just to give some quick background, certainly the quality of ingredients has a big play and an important part, I should say, of the products that they're made into ultimately. And certainly flavor quality of foods is known to be a major driver of food acceptance and dietary patterns. And in my opinion, flavor, I think, is underappreciated when it comes to healthier lifestyles. For example, a more plant-based diet, more sustainability, healthier, you'd say, dietary patterns. A lot of that really, I think, in my opinion, hinges on acceptance of these products. And people generally eat what they like, not, is an important part of how they select food and their dietary patterns. And so, to me, making healthier choices more less difficult, more palatable is certainly a strategy to elevate health and wellness initiatives and things like, looking at plant-based ingredient growth, opportunities and diets. And so, in this case, thinking about, plant-based proteins, certainly one of the goals of generating these materials is to create a protein source. This plant-derived versus animal-derived, but certainly known to have a lot of undesirable traits. In other words, you just want the protein, but as you take the protein away from the pea, in this case, if I'm looking at pea protein, it's a challenge actually to create a very bland, neutral product. And so, maybe when I think about flavor chemistry or flavor research and things that are related to perception, just maybe create a little bit of an overview of what is how do we think about flavor perception, and what then drives analytical methodologies that try to understand your the positive and or negative attributes of a food product. So with flavor, really three different modalities. We're in olfaction. Most flavor research has focused on smell. Odor and aroma, and it's maybe had some kind of thought that aroma is the primary driver of flavor. I would argue against that quite a bit, and that certainly aroma is an important part of perception, but so is gustation. If you think about sweet, bitter, salty, these are very innate traits to humans that very much direct product formulations and acceptance. And so I think overlooking those attributes to me has been a limitation of a lot of flavor research previously. So if I'm trying to, again, understand pea protein and I'm just focused on aroma, I'm probably not getting the whole picture, if you will, and understanding of things that are important for perception. The third one is somatosensations, the idea of tactile cues, textures that are being perceived by protein materials, for example, insoluble components, even soluble components. So it's really, when you think about perception and understanding flavor chemistry, you really need to think about this more holistically in our view, in my view, and that, and one of the limitations of a lot of prior research that relates to, say, pea protein or plant-based proteins, it's just solely focused on aroma. And I'll try to dive into a little bit of why I feel that way. But again, you have to think about, I think, flavor perception more holistically to really help elevate these ingredients in better ways. So if I'm going to dial in, looking at pulses and what comes from pulses and what we might make from peas, I guess more particularly, and the challenges. So you have this pea. If you ate a pea, you would have a flavor of a pea. And of course, a goal of making the protein is to strip away any endogenous flavors, because anything that's really there would be considered almost off flavor, right? So the idea is you just want the protein and not the flavor component in a sort of general sense. And, protein powders, including milk protein powders, have been studied quite a bit as it relates to stability. Even during processing and generating a powder creates, you have to create, a lot of times evaporation. spray drying and other processing that can catalyze chemistry and instability, such as lipid oxidation that can occur even, of course, during storage, or lipid Maillard reaction, say during heat processing, and alter, those sort of materials in ways that, again, are not bland, but generating things that are generally not thought to be desirable for product formulation. What is less known, and I'll talk a little bit about this, is these off tastes. Bitterness, umami. Umami might be great if I'm taking a pea protein and trying to make a meat analog, but less great if I'm trying to make a beverage. So those are some things to consider. Bitterness in general is aversive. Humans can grow to like bitter, for example, in coffee. And there's actually been some really interesting work that, because caffeine creates if you will, a dopamine or a reward, in that regard, that you can adapt a little bit easier to like maybe aversive attributes like caffeine. And so there's been some connection there. But anyways, the point would be is that, that these, pea proteins have a lot of different chemical stimuli that are, say, impacting on flavor perception. And, the goal is, how do we understand them to a high enough level that enables us to generate new processing methodologies or ways of storing them that create the more optimum products that are just more accepted, and that of course allow for more consumption and ultimately impact, right, if it's sustainability and or health. One of the things that's probably less appreciated about protein in general, but certainly relates to plant proteins, is flavor interactions. And so, when it comes to when I add different protein powders to a formulation, often the flavor that's in the product, that is the desirable flavor that you're maybe as part of the product formulation or just as it's made, the protein will interact with these flavor compounds that are there and alter, if you will, and then create an imbalance or alter the quality, a lot of times in negative ways. And so there's just not a lot of good understanding on how protein interacts with flavor molecules. So it's not just their endogenous, say, off traits. How do I remove them? But even when I put the protein into, in this case, food product, a beverage, how is it interacting with the flavor molecules that are there in a way that I can control that and ensure that the flavor is not altered in a negative way? We're going to talk about both of those. And so, let me just look at make sure I'm not going to go too far over time here. So, again, just thinking about origins of things, you obviously, as I mentioned, have, endogenous compounds that are in the pea. If I consumed a pea, what's maybe endogenous to the pea. You have a lot of enzymes that even when I'm eating a pea will generate flavors as I'm masticating it. They're not maybe in the pea itself, but actually as I start masticating, they generate things so quickly that as part of perception. If you think about harvesting conditions, like all these can have impacts on the quality and the product in a way that influence flavor or off flavor in that regard, and processing and storage and all the things. So all these are all pieces of you'd say, of the, if you will, the processing pipeline in a way that is influential and are known to influence the product quality. So I'll talk very, very quickly about my program. I'm going to define this a little bit just up front, is that a lot of work in the flavor world focuses on what's called sensory-directed methods. In other words, I'll take pea protein powder and I'll separate it out and look at where my nose responds, and then use that as a guide to say, oh, what is important to flavor or that off flavor of that material. And so in other words, I'm looking for what's called an agonist. I'm smelling. I need to have something that has a smell. Okay. And certainly is an important part of understanding some of the building blocks of perception. The other part that we in my lab have really been the last 10 years working on and have pushing a different methodology, if you will, a complementary methodology, is the idea of adapting from maybe a common term that is used is metabolomics, which is some kind of, you would say, a terminology is sort of as this untargeted, non-targeted chemical profiling, some kind of statistical analysis to now connect this chemical profiles to some attribute of interest, in our case, flavor. And one of the reasons to do that is to recognize that, that a limitation of the sensory-directed methods, that by look at molecules individually is not always predictive of how, when I'm perceiving a flavor, which is a complex pattern of molecules, doesn't always predict that behavior. And so using complementary methods allows us just abilities to think about flavor chemistry and you would say in more comprehensive ways, and really think about things that modulate or things that are affecting liking. And I'll just talk about that in some context as I work through my presentation. So, one of the things that is interesting about pea protein and soy and a lot of the related you'd say products is they're often characterized as thought to have beanie. This is going to be a lot of how the product is manufactured and just other aspects to it. But what I wanted to show you here is that, if I look at this as the sort of general 7 attributes that a descriptive panel would, try the product and come up with a lexicon and train themselves around different main attributes that they're perceiving in these, materials. And certainly beanie is one of them, right? One of the high ones. And this is we'll call it the protein powder, as it's spray dried or manufactured. But as soon as you take that pea protein and you, for example, UHT it or go through some thermal treatment, that beanie goes away actually, and it turns into other things. And not that oxidized and cardboard and sawdust are any better, or maybe other unique negative attributes generally thought to be right for products. Because often we think, oh, we got to get rid of the beanie. And I think the question always is that beanie in the raw material, or does it actually show up in the final product? And if it's not in the final product, then probably chasing at the raw material maybe is a little bit disconnected. And so we just got to try to, I guess, understand ultimately, what molecules are driving these attributes, that now relates maybe to the product of interest instead of the ingredient at times, and help us to kind of untangle some things. So if I'm just always trying to suppress beanie, but beanie is never an issue, if I'm thermally processing it, then probably we should be thinking about other mechanisms, right, that are at play and ways to think about product innovation. So, I'm going to talk about this again, where I go through, and this is what we'll call a sensory guided approach. We certainly use a variety of different methodologies in my program, but just to give you some, I had a couple master students do a little bit of work on pea protein, and to give you some quick outcomes of that work. And so, basically what in flavor research, what we're trying to do is, if I can start from the left, is think about how do you, isolate a good representative profile, a volatile profile of the aroma. We then go through what's called GCO, and basically we'll smell the effluent and identify actives by where we smell the peaks, in that case by human panelists. We then quantify those compounds. Often what is done is you will then look at the concentrations and match it to what's called a flavor threshold. And then from that, select ones that are above threshold is thought to be more important to perception, and then recreate these things into models and try to say, hey, have I got enough of the information that is representative of the attributes of interest? And that's the general workflow. If we sort of bridge forward a little bit, we just look at, again, some of my comments on the qualities of, in this case, pea protein isolate. Again, if I look at the control being, like a newly made pea protein, probably within 2 months, stored relatively well, cold, and I'll talk about that a little further. You have these list of compounds here that are thought to be, aroma molecules that are perceivable. Many of them above threshold, okay? And you'll have ones that are obviously like lipid oxidation products, and others that are maybe more Maillard type products that are derived from different method or mechanisms or pathways that just come from me taking pea and processing it into ingredients, right, in that regard. But I guess the point that I'm having you, if I have one, is that when we go through, in this case, the processing step is UHT processing. You can see that in this case, just by the color shading here, from sort of light to darker is increasing intensity of that peak or that compound, right, based on the peak area or the concentration, that you see quite a change in the profile. And so one of the things that we have to think about is not just controlling the pea protein itself as a powder, but the precursors that are in that protein powder. Because ultimately, when I make a food product from it, I have to consider the endogenous compounds, but also these precursors, because I want to minimize things generally from being formed, okay, would be the approach. If I age it, so now that sits around, maybe for 2 months, even at refrigeration temperatures, you'll see compounds changing as well. You'll see, in this case, some compounds going down, they're getting degraded. others that are increasing, okay, in this regards, right, which is sort of interesting. And so, again, this idea that you just don't have a protein powder, you're going to go through a number of steps that are part of the food, manufacturing process and even storage. And all these have implications. If I'm going to set up pea protein to be an ingredient, how do I, in I guess you'd say in one ideal world would minimize anything to begin with, and nothing forms from it, at least negatively is forming during thermal processing and ultimately during storage till consumption. And to give you a little bit of that, thought on beanie again, right? So what we can do is we can take, again, as I showed you this initial, what's called the spider plot, but again, beanie being a highlighted aspect to a lot of these legumes, and and that in this case you have beanie. And what we've done actually is we've looked at the compounds that are formed during the UHT processing step, and we add them to the control, okay, the one that is just the protein powder, and this is a beverage. What happens is if you look at this and you do this, so if I take this beanie, you can't see it, but on the one on the right, I got to remember, you can't see my mouse here, but the sort of darker orange color on the right, if I start adding compounds that are formed by UHT processing, that beanie goes away, and yet those molecules are still there. It's just that they start shaping my odor qualities differently. And so, it's not beanie that is the major attribute anymore, but as I mentioned to you, it starts transforming into other things like oxidized cardboard and sawdust, which obviously have connotations of negative attributes, and would not be desirable. And so, again, this idea that if I'm just focused on beanie, it may not be playing a major role in a final product. It may be in the raw ingredient, but not in the final product. And you can see a lot less changes are occurring during aging, but still some are occurring in that liquid beverage during that time under those conditions. One of my other master students did some work on just looking at storage, and not a lot of work has been out there on if I have a pea protein powder, for example, how do I store it? And so some very quick, standardized ways of looking at stability certainly are looking at the water activity as well as just temperature. And so we can kind of take a couple of pea protein powders and sort of see how they're behaving under these different, say parameters, and keep one, for example, stored at -40 as our control, which we'll call unaged. Certainly there could be some, but they should be minor, right? And if we've looked at that in general, I would say there's minor changes occurring, under those conditions. And what I can basically just highlight a little bit for you as I'm looking at some context and some bigger picture thinking is what I'm showing you here on the in this case my y-axis of both of these is the degree of difference score. Okay, so what this is basically looking at is people smelling these and giving some context of how different they are. Sort of an overall magnitude of change. Okay. So in this case, what you can see here is, that obviously, as you might predict, the water activity at 0.5 and at 37, sort of a little bit more extreme, but certainly not too extreme in a lot of warehouses in the summertime and many places, all the time. Depending on where you are, if you're in a tropical region or a warmer region, that you can have quite a bit of change in the flavor. And although I don't put this up here, I believe this is like 8 weeks time period. I have to go back and look at the publication, but somewhere around there. And just that you can see quite a bit of change in the stability of those protein powders sitting as a powder, say as they're shipped and then they're stored in a warehouse prior to being used as as ingredients, that they can have that you need to think about their stability or their flavor quality. You need to think about how do you keep them stable, right, during storage. And if we look at this data a little bit more, I guess some insights here, we can look at some of the main odorants. So on the left here, you have this list of compounds. Let me not delve in that too much. But I think what I would say to you is if I look at these different odorants that are in those materials, what is sort of interesting is that even though some of them have large full changes, like 1-octene-3-ol, which is certainly a well-known off odorant, a lipid oxidation product, would be certainly a mushroomy type negative attribute. It changed about 8-fold, okay, during storage. And if I look at it, it was sort of contributing the most, okay, to the degree of difference scores, okay, in that regard. If I look at the next, so all these compounds that are increasing, non-enol was actually the one that also resulted in a statistical change, and when I add it within the context of these other molecules, resulting in a perceivable change, right? And if I add all the molecules together, looking at them individually is sometimes a challenge because we're perceiving them as, again, as this mixture. And so what this is sort of showing you is that even though, for example, 2-heptanone, which changed fourfold, that molecule really didn't have any appreciable change when I was in a mixture. So again, one of the limitations of flavor research is that we look at sometimes you judge molecules individually for their particular odorant and above threshold. And this data is sort of saying, no, that's not completely true, that you can see larger quantitative changes among things that are known to be odoractive, but really when they're smelled with the mixture molecules, they didn't really have an impact. And so we need to have better understanding, I would say. If we really want to get, I would say, some innovation in this space, we have to start thinking about patterns of molecules, ratios of molecules, as they're perceived as a group, not as individuals, and not saying that that can't give you some guiding information, but it's not, I think, without limitation. And so thinking about data as you perceive it as a complex mixture, I would argue is something that needs to be more of. I'm just going to give you a quick snapshot of some work that is ongoing with one of my PhD students. And this is where, we're looking at, you can see a number of pea protein powders. This is what is actually the sample number, although it doesn't say it, that I'll tell you these are pea protein powders, pea protein isolates, I should say, in beverages. And we give them to, I want to say about 130 panelists and look at their liking, okay? And what you can see is they're liked quite differently, okay, from across them. There's statistical differences in liking. And then what we're doing now is actually taking the aroma profiles and doing multivariate analysis, in this case, we'll just say PLS, and looking at what are the compounds in that mixture that is really impacting liking or disliking. And so the goal of that is we're using this sort of, again, to get away from more like a flavor oaks approach. What are the molecules in a mixture that are really impacting liking instead of just looking at them individually? And I think, to me, this is something that I think would be helpful. If you will, you have 40 odorants, for example. Are there 3 that are really the negative culprits? And so it allows us to more tap into those mechanisms in a more directional way and help suppress, if you will, their formation or control their formation in a way that results in higher acceptance, right, of these products as they're used for beverages or other, food applications. So let me shift gears quickly and now and just talk about some work we've done on taste. Pea protein certainly, again, has some, as I mentioned, attributes that are, known to be negative from an aroma point of view. But what about the taste? And if you look at, again, just a list here of 5 commercial pea proteins that were sourced, and it's sort of looking at, I guess, across those, are the umami, that savory component, or are they bitter? And we do see that we can find these ratings sometimes pretty subtle, and other times less subtle, more meaningful, right, in that regard. And so, again, the idea is what would be, underpinning bitterness and umami in pea protein to give a molecular origin that now allows us to think through, optimizing these products and obviously in a pretty granular way. And so if I look at these again, I'm just going to give you an example, a pea protein. So what we do in the program here is sort of similar to what we do at GCO, is that we'll take an isolate and actually run it through an HPLC column, fractionate it, and actually taste it, and do this in a food grade way. And so we're very careful about our protocols and how we go about this. I read my papers if you're interested. But what ultimately I'm showing you here is if I just look at this first dimension, you'll see here that in this case, the third fraction is showing bitterness among all the different fractions that were collected. And so that fraction will then go through a second dimension of separation. What you see is that second dimension go through a different column, different column chemistry and sometimes mole phase to create orthogonal separation ability. And we keep going until we get down to ideally single molecules or high purity, in that regard. And that is not trivial. And we're sort of using this as a sensory guided approach again towards discovery. And so this bitter motif that we found in pea protein, I'll give you just a little bit of in this case, the MALDI FT-ICR-MS analysis. And what we're doing is just using a very high resolution mass spectrometer for high molecular weight moiety that creates the resolving power we need and then allows us to create from that, it can weigh it so well that we get a formula, right? A molecular formula. It can say, oh, if it's this weight, then it's consisting of this many carbons, hydrogens, nitrogens, oxygens, and sulfur, right, in that regard. And so it gives us a lot of insights into what it would be. And from that formula, this gives you the swagger of a peptide. And so what we can do is we go forward and we'll do de novo sequencing. If I'm doing an unknown analysis, one of the things that mass specs can do really well is de novo sequencing. In this case, we use collision-induced association, and I won't get into all the details, just to highlight some things. And ultimately, what we do is we, in this case, identified this p-albumin type 1b, peptide sequence was identified as being bitter. And so, this creates now a molecular signature. Somebody can monitor this in pea protein and look at, maybe ways to chop it up further if that would help to debitter, for example. But it creates an understanding, again, of the molecules that are in these materials and how they're ultimately impacting perception. This particular amino acid has these 3 cysteine residues and creating these 3 intermolecular bridges is what we would say based on what we expect from nature. And then what we would also do with this is actually, this has never been tasted before. So in my lab, what we'd actually do is we'd measure the concentration in the pea protein isolate, but also what is the threshold of it, okay, in this regard. And so this is, again, based on certain concentrations of solutions, and it's going to depend on how much protein powder you put into your sample. But what I can say is that this one isolated peptide, again, for the first time shown to be bitter, was certainly well above its bitter threshold. And bitter is probably out of all the flavor attributes, probably one of the more directional ones that relates to disliking, okay, in a general sense. And so certainly gives some kind of cues into regards to how do I think about, product innovation in that regard. The other aspect that I'll go through here is umami, right? So, umami, again, is this well-studied, everybody knows about MSG, monosodium glutamate, and certainly one of the main you'd say drivers of umami perception, for a long time given a bad sort of stigma. I don't think science supports that at all, actually. And you have major sources of MSG in your diet. Tomatoes is a good example. This is why, maybe the Italians were clever with their tomato sauce. And things like Parmesan cheese, have large amounts of MSG, amino acid that's in its salt form. And because it's in that salt form, you have a receptor that triggers onto that and is activating that receptor, and then your brain says, "Oh, I have umami," and creates this this sort of savory, desirable perception. So, anyways, as I go through, what we do is I won't spend, but left to right, we're taking in this case the PPI and looking for umami and separating it out, pulling it apart into individual molecules. And what you'll see again is in fraction 1, we have umami, and what that sort of implies to me is something, if this is a reverse phase column, that it's really hydrophilic and likely to be at least MSG, and we're aware that it's there. So we go forward and we keep separating. Okay, and now I have 1,8 is where most of my umami is. And then when I go to the third dimension, I have a little bit of umami at the front, but then I lose some of the intensity. And so what I can say is, okay, we're kind of aware of this, but it's sort of implying that there's some enhancers, okay? Things that by themselves aren't umami, but when they're mixed with, for example, MSG, and this is some chemistry that's well done, in the field. So we look for these, and certainly what do we identify is actually the 5' nucleotides are certainly known, but probably the more common ones, I would say IMP or inosine monophosphate and guanosine, GMP, are also probably more well characterized as umami enhancers. Ones we identified are UMP, uridine, and adenosine were in those isolates. And what we can nicely show is we'll quantify them right in those samples and get some information about, for example, the pea protein A that I list to the second on the left, the second column in, had a lower intensity, you can see, of umami. And it had very low levels of those enhancers. When I look at pea protein E, those enhancers going up. The MSG is in both, but it's right around threshold. Thresholds are wildly ranging with MSG, and I suspect for good reason. It depends on probably how they were formulated, the pH they were tried at, a whole host of things. But regardless, one of the lower, you'd say, levels of MSG is around 54. Thought to be sort of where people start to recognize in general. Now you have to remember that's 50% of the population. There's a bell curve there. But what it's ultimately saying is that MSG is likely not a major contributor to umami in pea protein. And so how do we test that? Well, we get these quantitative data. And if I'm looking at this graph here, what I'm going to show you here is we take pea protein A, which had low amounts of that umami, and we add back the levels of those enhancers to the pea protein A, and we'll call it basically we'll call it modeling pea protein E in that case. So, maybe if you look at my slides a little bit, if I look in the upper right corner, we take the isolate A, which is low umami, add back the levels of those enhancers that are in pea protein isolate E to A, and see does it mimic E. Okay, so a way to do what we'll call recombination in the product, not by itself, not singly, but actually in the product. Does it actually generate these sensations? And the answer is yes. And so it's an easy one to show you here that both AMP and UMP are actually, I would say, contributing to the MSG level, although it's at threshold, because these enhancers are there, it is driving umami perception. You can see on sort of the main graph here, again, the average umami intensity is increasing from like around, 1.5 up to around 8 on a scale, on this 10-point scale. And certainly demonstrating to be causative in regards to when I try these different pea protein powders, why am I getting umami perceptions? But really because of these enhancers, okay? And that can be, in this case, sometimes desirable and sometimes less desirable. All right, the last piece, just to kind of show you a breadth of some of the things we're working on, and I'm almost done with my slides here, is that one of the things that I would mention is that we certainly are focused on, again, understanding molecular compositions of proteins, and in this case, pea protein isolate, and what is sort of driving, different components of their flavor profiles, and a lot of times things that are adversive, in that regard, or maybe things that are actually desirable. How do we make them even, maybe mask some of the negative attributes, right? So in this case, I'm going to move forward and just talk about some more recent work with one of my other PhD students, and really looking at binding. Again, if you were to take a protein and mix it with flavors, it's really hard to predict how it's going to alter the flavor composition. We just don't have a good handle on these interactions between flavor molecules and protein molecules, and how they're interacting with each other and ultimately affecting the vapor pressure, or if you will, how much is now released to my nose when I'm consuming these products. And so, we've been working on a few different, I'm going to release some papers on this, I hope, with a student relatively shortly. And I'm just going to show you a piece of this. But what's kind of cool is what we're able to demonstrate is how do we look at in this case, if I just look at the graph on the left, I'm looking at two different samples, okay, that are ranging in some attribute of that pea protein, and I can show how they're changing the binding behavior. Okay, so really starting to lock into what is the physical properties of protein that alters binding. So what you're seeing on the y-axis is how much that flavor, if I add 100 part per million or 100 parts of it to a flavor, what it's basically saying is 40 parts of it are being bound by the protein and therefore no longer available for you to smell. In the sample 2, it's showing you around 80. So most of it is just being bound by protein, and you no longer can perceive it because it's suppressing it, if you will, in regards to your perception. And so a lot of these desirable molecules that are part of your liking, you don't want them being, if you will, absorbed by the protein in a way that limits their perception and therefore alters their flavor quality or makes it more negative. And when I'm sort of showing you some really cool stuff, at least in my mind, is on the right, we're now working on NMR methods to actually look at binding behaviors as well. And I'm just showing you the analogous samples 1 and 2, and we're actually using an NMR and developing methods for, say, measuring the amount of protein that is bound to allow us better ways to really understand mechanisms and ways to monitor, if you will, flavor binding, in a way that is hopefully more meaningful and provides more context for the field. So, giving you again some quick overviews of the program and some things we're doing here, but ultimately the goal, as I mentioned to you, is how do we understand flavor more holistically? What is off odors and off tastes? What are these individual molecules? How do I understand how they're being generated? Maybe during manufacturing, or ultimately in the raw when the powder is first made to when it's stored for a certain amount of time. How do I sort of think about all these pieces to again optimize the quality of these materials so when they're ultimately made into food products, they're not you would say detracting from their quality. And that goes from that to off tastes and talking about, in this case, bitterness was one of my examples, or umami, The newer one I hope to put out in the next, later this year would be really focusing on what is really among all the molecules that are adversive. Like if you look at the individual attributes, a lot of them seem offensive. But again, we're not smelling them individually, feeling as a pattern. So the goal is can we sort of decouple these complex patterns and really focus on ones that are meaningfully impacting liking? And so we have some ones that actually seem to be improving liking and some that seem to be the culprits for disliking. And so we're working on trying to decouple that a little bit more. And I think really get away from just looking at individual molecules to more what is affecting consumer behavior, which I think would be a step forward. And as I mentioned to you, lastly, I think an area that still has a lot of room for growth is how do we understand these flavor protein interactions, ultimately to understand those the physical chemical, you would say mechanisms or properties of proteins that are affecting binding mechanisms, and really to put that together. And then that really allows us to think about protein sources, plant protein sources, and I think in a very meaningful way to really develop higher quality products from them that really help promote growth in the industry. And so, with that, I will stop and happy to address any questions.